Okay, so today we're going to be solving a problem that asks us which of these molecules are polar. And to do this, we first must overview some things so that we can solve. So first, we need to draw the Lewis structure of each of these. Then we're going to identify the bond dipoles using the different electronegativities between each atom. Then we're going to identify the net molecular dipoles based on the molecular geometry of each of these molecules. And note that you can determine the polarity of the molecule by looking at its domains, not just its dipoles. Non-bonding pairs, but not always, can help determine if the molecule is polar along with the dipoles. So first we're going to look at SO3. And if we look at the periodic table, we see that there are 24 electrons. And for 24 electrons, we're going to start by adding around the outside atoms, not the center atom. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. Okay, so this molecule has all the electrons needed, but the central atom S does not have an octet, so we must fix this. And to do that, all you have to do is draw a bond that consists of 2 electrons, and you're just going to scratch off these 2 electrons, making a double bond. And in doing this, it gives us multiple resonant structures of SO3. So we can have one here, here, or here. But we also have a real molecule, or the resonance hybrid, which means that we have a sharing of bonds between these 3 atoms, which is 1 1/3 bonds. So now that we know how to draw the structure, we're going to go to look at the partial charges and the bond dipoles. And to find the bond dipoles and partial charges, we're going to look at the electronegativities of each of these atoms. And looking at oxygen, we know that it's 3.5 and sulfur is 2.5. So we're going to get the net electronegativity, which is 1. And because the net electronegativity is greater than 0.4 and less than 2, we're going to have a polar covalent bond between these 2 atoms, which gives us partial charges. So we're going to draw that in. So oxygen is greater than sulfur, so sulfur is going to be positive. And oxygen is more electronegative, so it's going to get the partial negative charge. And now that we have the partial charges, we can draw the dipoles. And all that a dipole is the more electronegative atom is going to get the arrow side. The plus is going to go on the positive atom, arrow on the negative side. And we're just going to draw that for every single atom. And essentially all of these dipoles are the same. Okay, now we can look at the net molecular dipoles. We see for this this hybrid, or not hybrid, real molecule, that it has 3 domains, so 1, 2, 3, and its molecular geometry is trigonal planar, which means that there's 120 degrees between each bond, and the domains are the same. So since all the domains are the same, this molecule is nonpolar, and the dipoles cancel. So because they're all the same, they're going to cancel. Now for oxygen and 2 fluorines. We know that there's 20 electrons looking at the periodic table, and all I did for this one is started by adding around the outside atoms. Then I brought it in towards the middle since I had 4 extra electrons. And so we know that it has all the electrons needed, and every atom has a satisfied octet, so there is no resonance for this structure. So we can go straight to the partial charges and the bond dipoles. Oxygen has 3.5 electronegativity, fluorine has 4.2, so we subtract, we get a 0.5 net electronegativity, which again is greater than 0.4 and less than 2, so we have polar covalent and partial charges. So oxygen is what? It is less than fluorine, so we're going to give it the positive partial charge. Negative because fluorine is more electronegative than oxygen. And now that we have that, we can draw the dipoles. And all we have to do, positive side of the dipole on the oxygen going towards fluorine. And we're going to do that the same on the other side. Now we can look at the net molecular dipoles. Now this structure is different. We have non-bonding pairs. We have 1, 2, 3, 4 domains for this structure. Its molecular geometry is bent, even though its domain geometry is tetrahedral. We have 2 non-bonding pairs bending this molecule. So these bonds don't cancel like you think they would, like the last molecule. They actually add. Since the non-bonding pairs point them down, they're adding down. So we have not all of these domains are the same. These can't be canceled. They add, so if we look at the rule, at least one different domain means that this molecule is polar. So the domains don't cancel, so oxygen and 2 fluorines are polar. Next molecule, we have Be and 2 Cls. We have 16 electrons. We start by adding on the outside. We have 2, 4, 6, 8, 10, 12, 14, 16. And you may think, oh, beryllium doesn't have an octet. Well, actually, beryllium is an exception to the octet rule, so it doesn't need to have a full octet. So there's no resonance for this structure because there are no double bonds to be shared. So now looking at the partial charges and the bond dipoles. Alright, beryllium has a 1.5 and chlorine has 3.0. So looking at my little calculations, it's 1.5. Again, that is between 0.4 and 2. So it's a polar covalent bond between these 2 atoms and its partial charges. So can you guess what beryllium is? Does it have positive or negative? It has a positive because it is less than chlorine, and the chlorine has the negative because it wants those electrons more. So with that, we can draw the dipoles. Positive side on beryllium, pointing towards the chlorines. And these are the same because the domains are the same. So we're going to look at the net molecular dipoles. We have 2 domains, and the molecular geometry is linear. So that means that these dipoles are going to cancel, and all of the domains are the same. So this molecule is nonpolar, and all the domains all the dipoles cancel. So we can go to the next structure. We have carbon and 4 chlorines. We know that there's 32 electrons in the periodic table. Well, by calculating, there's 4 chlorines, which is 7 times 4, and carbon is add 4 gives you 32. So we start by adding all the electrons on the outside. You have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. 16 areas of electrons times 2 gives you the 32 electrons you need. So we have all the electrons needed for every single atom to have an octet. It's satisfied, so there's no resonance because there's no double bonds. And now we can go to the partial charges and bond dipoles. We see that carbon has 2.5, chlorine has 3. Subtract its 0.5, and again it has polar covalent bonds between these 2 atoms, which gives you partial charges. So carbon is 2.5 and less than chlorine. Again, it's going to be positive, and partial negatives on all the chlorines because they want those electrons. Now, for the dipoles, like you learned before, positive end on the carbon, positive end going towards the chlorine. Oops, wrong. Positive end towards the carbon going towards the core. Okay, so now we can go to the net molecular dipoles. We have 4 domains. The molecular geometry is tetrahedral. Looking at this, what do you think? All the domains are the same, all the dipoles can be canceled out, so this molecule must be nonpolar because all the domains are the same and they cancel. So, last but not least, we have ozone. And we know that on the periodic table, 6 times 3 gives you 18. So we start by adding all the electrons on the outside first. But as you can see, oxygen needs an octet. So 2, 4, 6, 8. We got that by canceling one of these pairs and just making a double bond. So because of that double bond, we now have a resonance structure like we did in the beginning. We have a bond here, a double bond here, and that means the hybrid gives you 1.5 bonds sharing between these two oxygens. We can go to the partial charges and bond dipoles. They all have the same electronegativity. Canceling gives you 0. These are nonpolar covalent bonds, which means that there's an equal sharing of the electrons and no partial charges. So we're not going to draw any dipoles on this molecule. We're just going to go straight to the net molecular dipoles. We see that there's 3 domains. Don't be fooled. It's not 2. We have this non-bonding domain. And because we have a non-bonding domain, what do you think that's going to do? It's going to bend this molecule, pushing them away from the linear state. And it's going to give us not all of the domains are the same. So like I told you in the beginning, it could be polar if at least one domain is different. So one domain is different, bending this molecule, and it's giving us a polar molecule. Yes, that's it. Okay. And now for common mistakes. Well, first, let's look at this. We saw that SO3 was non-polar because all the domains were the same. OF2 was polar because we had 2 non-bonding pairs on the oxygen. Beryllium dichloride was non-polar because the domains were all the same. Now, carbon and 4 chlorines had all the same dipoles, so they were non-polar. And ozone was polar because of that non-bonding pair. These non-bonding pairs don't cancel out because they go like this compared to the two molecules that will come down here. So they can't cancel each other out. So now looking at common mistakes. We see that not drawing the Lewis structure correctly can make you solve this problem incorrectly. You need to add the electrons to the outer atoms first. Also, don't forget about the non-bonding pairs. They're very essential to determining if the molecule is polar or not. And also, you need to make the correct resonance structures if you are ever asked to do so, or even when making a molecule, because that can help you determine molecular geometry or what the actual molecule looks like.